this is going to be the final session for the course, and we have provided you an introduction to all the different parts of a digital system that is going to be required to build a simplistic computer. And in this session we are not going to introduce anything new, right, or any new topic. Rather, we are going to give you some more insights about the entire course and the various components that were used, right, in terms of logic, like digital logic and the various techniques and so on, so that we have a overall end-to-end understanding of computer systems, because the name of the course, as it suggests, is computer system design, right? And a computer system design course is typically intended to give you an introduction of how a processor works, which is typically intended to be followed up by a more advanced course like an computer architecture, and further followed by compiler design or operating systems and so on, right? But in the interest of the time, as well as the primary focus of this curriculum, which is data science, right, we don't want to go into even further details. This is going to give you an introduction that is required at an undergrad level for computer systems, and operating systems is going to be offered as a follow up, right? So the bridge might be a little bit more concepts in terms of memory that is going to be required as a part of architecture. So that is something I would recommend in the recommended textbook that you are anyway following, right, which is Morris Mano. We have covered pretty much to some extent the themes that are there in Morris Mano. There was one more referred textbook which was the Harris and Harris, and there it is going to contain some chapter on memory organization or more details of the control logic design that we have studied in this class. You can refer to those chapters. That is going to make you better prepared for taking up courses like operating systems, right? So now let me kind of rewind the entire course, and let's say go back to the one of the first lectures, right, where we were trying to design computer systems. And as I told you, computer systems at the core or at its heart, it is going to contain some kind of a general purpose processor typically, which can execute software, right? And that is the flexibility that a processor gives you. It can execute any code that can be written in terms of its instruction sets, right? So any algorithm or any computational problem could be executed on a general purpose processor. And in contrast, you can also have application specific hardware, right, which is not really a processor, but let's say we design some kind of a special kind of a counter that does a counting sequence, right? So it is not flexible, you can't really change, and it's not programmable, which basically means that you cannot write a piece of software that is going to change the behavior of the circuit, right? Rather, once you build the circuit, you can't really change that. So those are application specific hardware that might be useful in some cases, but although we have touched upon those concepts, our main goal is to kind of understand how a processor works, right? So typically the flow would be like this. So we are kind of intended towards general purpose processors. Okay, so anything that we can compute on a processor, it basically starts with a computational problem. If you recap from the very first slide or the very first few sessions, we always spoke of a computational problem, right? So there is a computational problem. Okay, and by computational problem, it has a special meaning, right? If you really take up a course on theoretical computer science, they keep talking about Turing complete systems and so on. Without going into the nitty-gritty details or the technicalities of those terms, I would restrict myself to kind of give you a very simplistic argument about what is computational, something that you can compute, right? There is no ambiguity in terms of the results. So, suppose if I want to tell you that add these numbers, right, or what is the maximum value inside a set of numbers, or sort a collection of numbers, right? There is no ambiguity. Okay. So, that is very strictly defined answer, deterministic answer, and or let us say find out the shortest path inside a graph. So, all these are computational problems. Okay. And so, anything of that sort can be converted to some kind of an algorithm. If you want to solve this problem, you can have an algorithm, associated algorithm with it, right. So, this algorithm can be implemented in a high level programming language, right. That is something that you are already aware of. So, you can use a programming language of your choice, right. Typically, you can program this using C++ or Java or Python and so on. So, you have this, for example, you have some kind of a, I would write something like a pseudo code to implement the algorithm, right. So, after that, anybody who has been given a pseudo code can translate this pseudo code into an actually functioning code in a high level programming language, right, be it Python, be it Java, be it C++, right. So, this is like an abstraction that is being provided at this layer, that if you want to take input from the user, you know what kind of APIs to use or library functions to use, right. If you want to, let us say, initialize an array, you know how to do it in a high level programming language. If you have to do something repetitively, for example, you want to have a loop, you know how to do it in Python, you want to do it in Java, you know how to do it in Java and C++ and so on. So, there is a syntax or functions or libraries that your high level function provides, which implements or which realizes the pseudo code that you have talked about, right. So, you have this literal programs, right. You can basically call them this high level programming languages, high level programming. Okay. So, now this is an interface, right, that basically translates a computational problem into its high level programming language implementation, right. So, this is a realization of that. So, after that, now you write the program, and this program is again it is an abstract way to represent the code, right, at some sense, because this is going to be running on real hardware, right, and this real hardware is going to vary from platform to platform, because the program could run on an Intel x86 machine, right, or it can run on a very low end device like an Arduino. Many of you are familiar with all these different low end computing boards like Arduinos or Raspberry Pi, or it can run on a high end server class machine. All these are different compute platforms. However, they should be able to, given the amount of resources that we have in them, we should be able to run some kind of a high level programming language code, right. Is going to, we can program that initially using high level programming language, and then of course then comes the task of the compiler, right. So, you can take a compiler which is going to compile this code, right, for a target architecture. Okay. So, after this we had target machine where this code is going to run, right. So, this is another sort of interface, right, the compiler takes this high level code, right, and then basically knows the target architecture at which it has to deploy the code, right. So, the machine code that is going to run on the target architecture is basically provided to the compiler. So, I want to execute it on x86 let us say architecture, or I am trying to execute it on ARM architecture, right, or there are Power PCs, Sun, Spark and so on, right. So, these are the various kinds of architecture, right? RISC-V. These are the various kinds of architectures, target architectures that has to be provided to the compiler to convert the high level programming language into the machine language that is interpretable by the implementation of the said instruction set architecture, right. So, these are all ISAs, instruction set architectures. I will call that as target architecture. So, target architecture is basically some kind of an ISA or instruction set architecture. Okay, which could be x86 for example, which is one of the most common and predominant across all of our devices we use in everyday life, like our desktop computers, our laptop computers, most of them are probably following x86 architecture, whereas our mobile phones could probably possibly be using the ARM kind of architecture CPUs, like ARM ISAs, right. So, if you are running a high level programming language, let us say you are trying to do it in Java and trying to build an Android app, right, there are high chances that after you do the compilation, your Android app is running on an ARM architecture, okay. Whereas, if you write the same kind of a program with a GUI and it is running on a Windows laptop, right, there is a high chances that you are actually running the code on an x86 architecture, right. So, this is about our target architecture, and this is another level of abstraction where the compiler compiles the code at for a certain architecture, and of course, there is dependence on the operating system, because the compiler after the compiler compiles, there are phases like linking the program, loading the program, and there are issues with memory. So, of course, there is virtual memory and all these concepts that are involved, right. I am not mentioning it explicitly here, but at least I am saying that there is a big role of operating system to play for managing memory and so on, right. We assumed a very simplistic model of memory in our course, as well as in the kind of implementations that we were, or the simulations that we were doing. They were very simplistic, but in the real world the compiler may have addresses, or if suppose you want to do a system call, you are not taught about this, but let us say if you write a program in C where you want to allocate memory, right, dynamically. So, often you use malloc, right. So, how is this malloc going to be handled? You need a new chunk of memory, and this is not the compiler's job, right. At runtime, if you need memory, the operating system needs to provide you support, right. So, those are the things typically covered in an OS class, how the operating system also helps you in executing the program, right, helps executing the program in terms of various things, in particular managing memory, right. So, you also have to keep this in mind, and of course, this architecture is extremely important, because the machine code that is being generated by the compiler is intended for that particular architecture, right. And now, once you have the ISA, let us say you have an x86 ISA or a RISC-V ISA and so on, you can have various implementations of those ISAs, which are basically individual microarchitectures, right. So, after this, right, you have micro architecture realizations. So, micro architecture realizations. So, for example, in your ISA, suppose you have an add instruction, right. So, the ISA tells you that I have we have to execute an add instruction, right, or rather I would not say add, right. Let me have okay, maybe add is okay. So, I can have an add instruction, and these add instructions the registers that are going to be used is a part of the ISA. So, maybe I can have, as I told you, source 1, source 2 and a destination. So, the destination value of the final answer is going to be stored in the destination register, and the two operands are source 1 and source 2. Those are going to be added, the values in them are going to be added and put into that. So, this is an instruction, right. Now, the implementation of this instruction may vary, right, how exactly your CPU is built, right, whether there are any temporary registers that are not exposed in the ISA. Suppose you are using a ripple carry adder, or you are using, you don't have to always use a ripple carry adder. There are faster implementations of adders called carry look ahead adders, right, which are faster compared to ripple carry adders. If you just recall, from the least significant bit, you have to propagate the carry to the next stage, right, and every stage the carry propagates, right. It is basically going to introduce delays in executing the addition. The gate delays are going to add up, right, from the least significant bit to the extreme most significant bit, or the carry out, right. So, you can use a faster implementation, but that implementation detail is concealed by the microarchitecture, that is not exposed. Okay. So, what the microarchitecture exposes are sort of the APIs, right. The instruction set architecture is only going to be a set of APIs, which is kind of your instruction, right. So, how it is implemented, is the microarchitecture, okay, which is here. So, if you want to do a fast adder, so I won't say fast adder, let me say first one is a ripple carry adder, The other one could be something called a carry look ahead adder. They are going to both tell the same result, 5 plus 6 equal to 11, right. It's not that ripple carry adder is going to tell you 12. Okay. The implementation of a ripple carry adder and a carry look ahead adder is very different, right. But in terms of the results, if you want to have instruction set architecture says I provide addition in, let's say, 1 clock cycle or 2 clock cycles, whatever, right, that is not going to change. What is going to change is the underlying implementation of add, which is realized in the microarchitecture, right. So, we looked at a very simplistic microarchitecture implementation of an ISA, and which was very trivial, right. We only had 8-bit instruction, and out of that 3 or 4 bits was used as an opcode, and only 4 bits was used for the operands, which is very trivial and probably not very useful, but at least we went through the process of looking at how the microarchitectures could look like and what could be their potential realizations, okay, and at least the style is something that we want to follow, okay. So, now you can understand that this interface is really important. This is the kind of the heart and soul of your actual computer, right. So, the first thing is the compiler. The compiler converts your complicated program into a set of very simple instructions, and those simple instructions, I am calling it simple particularly in terms of RISC processors, where you typically have simpler instructions. x86 is an example of complex instruction set architecture, or like CISC processors. I am not going to delve into details, but typically you can think of complex instruction sets are instructions that can do a lot of heavy lifting work, right? In a single instruction you can do more complicated jobs. Let's say you want to do a floating point multiplication, or let's say some division, right? Floating point division that could be directly handled as an instruction in x86 architecture, or even something more complicated. Whereas in case of a RISC processor, which is a reduced instruction set computer, in those cases you are going to see much more simplified, more humble instructions that are probably not doing a lot, but you can use a lot of them to realize similar functionalities, right? As long as the instruction set architecture that you are providing can help you to do any sort of solve any sort of computational problem, you should not be in that should not be an issue, right? Maybe for example, multiplication is not present in my processor, I can just have add, but add could be used to perform multiplication, right? Because if I have a facility to have loops, there is no reason I will not be able to perform multiplication, right? Just that it is not going to be very efficient in terms of performance. The time that your program might take to perform one multiplication could be way longer than the other computer which directly either has a multiplication instruction or like a dedicated hardware for doing multiplication, right? So anyway, so the compiler, you need to understand that pseudocode to high level programming language to a compiler plus OS, which is targeted for the underlying instruction set architecture or the underlying architecture, and that ISA is basically implemented using a micro architecture, right? This micro architecture is basically your own design, your own implementation following a certain ISA, right? The ISA is basically like an interface, or as I call, or it's very popularly referred to as a contract in between the hardware and the software, okay? And as you understand here, this is the primary thing that we have learned as a part of this course. This is basically your digital logic constructs. So to logic, and in particular we have looked into two kinds of things. One was the combinational logic, the other one is the sequential logic. So in very simple terms, as long as our computer is concerned, what is happening in a clock cycle is typically the combinational logic, right? So the delay of a combinational logic can be computed in terms of gate delays. So you have some inputs and you have some outputs, right? And this is not going to be carried forwarded in the next clock pulse, something will happen, no dependency, right? Whereas sequential logic is something where the previous output is going to influence the next input or the next output, okay? The next set of inputs or the next output. So typically sequential circuits are going to have a feedback from the output to the input. So there has to be a memory element which retains the state, okay, of the circuit. So sequential logic, combinational logic, we are not, when you build the processor, there is nothing we segregate like this, right? So there are parts of the processor that are purely combinational in nature. For example, all the arithmetic computation that we do, addition, subtraction, or the logical computation that we do, and or XOR and all these things, right? Those are purely combinational logical constructs, right? It does not take n number of clock cycles to do this. They can take multiple gate delays, right? But gate delays are much smaller, right? Could be a few nanoseconds or like 10 nanoseconds, right? And you may have a critical path where you might be having to cross 3 or 4 gates in the worst case, right? So that is basically the delay of your propagation delay or the delay for your combinational logic. Whereas sequential logic, right, the entire thing is going to depend on the number of clocks that you want to provide to solve the problem, right? Suppose you have a we are building a counter which changes its count value, and if it counts from 0 to 10, you have to, with every clock pulse it is going to change the value, right? So you need 10 clock pulses, and all you need to make sure that to make the circuit run faster, you need to provide a clock that operates at a higher frequency, right? So within a given clock, whatever is combinational in the circuit is going to be ready, right? And you need to make sure that you are not providing the clock even faster than the speed your combinational circuit is operating, right? Suppose you are making some combinational circuit that in the worst case has a propagation delay of, let's say, 50 nanoseconds, right? And if your clock triggers at a rate which is faster than 50 nanoseconds, of course you will run into a problem, right? Because your previous computation, whatever you are supposed to do in a certain clock pulse has not been completed, you cannot issue the next clock pulse, right? So all these things were discussed, and I can kind of tell you the details of that, right? Basically whatever we have covered. So, and underneath of that, which we typically cover in some courses but not covered as a part of this course, is the concept of how logic gates, because this digital logic, combinational logic and sequential logic are made out of logic gates, right? Logic gates, which are your favorite gates like NAND, AND, OR, XOR, NOR, and so on. And you know that some of these are universal logic gates like NAND and NOR, which could be used to realize any Boolean function, right? Any SOP could be realized, sum of products. And these logic gates are basically built using transistors. Okay, so I did not cover that explicitly, but transistors which could be abstracted out, the microelectronics of the transistor could be abstracted out, and we can basically think that the transistor is acting as a switch, as a logical element, either it is on or off, right? So it can be abstracted as a switch, right? So either the transistor is on, so it will allow the passage of electricity, or it can be off, it is not going to allow the passage of electricity, something of this form, right? So suppose you have a like plus 5 volt here, and here you have a transistor element, and you basically have let's say ground here, okay, and you can, this is the value that you can read, right? Let's say some or you can basically reading here ADING, right? So now if you think of this transistor to be closed, means they allow, right, the passage of electricity, right, through some load, maybe may have some resistance here. So you are not going to see the same voltage, right, if you have it open, right? So if I have a circuit where this is open, right, this is the switch is open, it is not allowing the passage of electricity, okay. So in this case, if you, let's say, read the value, let me draw it a little bit in a better way. Okay, so in these two cases, one is the transistor is closed, is basically allows the passage of electricity, whereas in this case this is open, it is not, right? So here you will basically see 5 volts, right? And in the other case you will not see that, because the voltage drop is going to be somewhere else, okay. And this is going to be useful like in various combinations to create different kinds of logic gates, right? This is this could be used in various combinations to realize NOT logic or let us say AND logic, NAND logic and so on. Okay. So, these things were not covered in this course, and this is not something that you also have to kind of pursue to understand the rest of the topic. Okay. So, this is something that you can just, even in the reference book, right, Harris and Harris, they have a portion which is, I think, is chapter 1 or section 1 called the CMOS logic transistors, where they talk about these two kinds of transistor, PMOS and CMOS, which is going to be used together to implement some very simple gates, right. They start with a NOT gate, and then they can use it for building an AND gate, and they will show you how to make more involved gates like an OR gate or an XOR gate and so on, right. But this is enough to know that underlying the logic gates, you basically have a network of transistors. So, you basically take a few transistors, and those transistors together can be used to synthesize logic gates, and that was another abstraction. So, as I am drawing the different abstractions, when you talk about logic gates, you do not think about how it looks like underneath, right. This could be CMOS or this could be something else, okay. But this is an abstraction. You do not know how the NAND gate is implemented, you do not know how the AND gate is implemented, you just use the AND gate, and you think that if you put positive logic and a positive logic, the output of the AND gate is going to be 1, 1 and 1 is 1. You do not know how it is getting done, and we are abstracting it out. And even if you think of a transistor network that I told you, that the switch could be on and off, if the then I can connect a bulb, whether the bulb is going to glow or not glow, right. I drew a resistor load, right. So, the current is going to pass through that or not pass through that. So, that is always an abstraction. Underneath the transistors, you can always have the underlying microelectronics, why the transistor is acting as a switch, right, because these are all abstractions. So, one of the things that we have in computer science, that this is basically like a big onion, right, and you basically take out the layers layer by layer, right. Once you remove the layer, you go to the next layer of details. Once you take out that layer, you go to the next layer of details, right. So, I kind of gave you a picture of a computational problem that you have an algorithm to solve, how this is going to be converted to a pseudocode, how that could be realized in terms of a high level programming language, right, because this is an abstraction. When you write a pseudocode, you do not really have a real implementation. You have an idea which is of course mathematically rigorous, unambiguous, etc., but in order to realize that, that is going to be run on a real computer, something that could be compiled, you have to use actual library functions, right, or real header files that has been somebody has implemented, and you have to use those header files to use those library functions, right. And then once you write the program, right, you probably write it in an IDE or some kind of a text editor, and you think that is the program, right, but that is not a program that a computer understands, right. You write include stdio. Include is nothing to do with a computer. This is just human readable text, right. You write printf hello world, right. Hello world is just a text that could be read by us, right, or a printf. So, printf is something which is very involved, right. A processor needs to send out the text hello world to a display unit, right. There are so many complicated things that are going on just to print out hello world to the screen, right. So, all those things are abstracted out from the high level programmer. He or she is just going to be bothered till here. Once and compilable code is generated, assuming that is of course to some extent optimized, but even if you do not optimize, it does not matter. It is just that the performance is not going to be as great, but this is a clear boundary where the compiler takes up your job, right, and the compiler on which is basically running on a certain OS and or the target architecture as well as the target OS, it is going to compile the program and then execute the program in that environment, right. So, compilation is, of course, you can do it without even running the program, but to run the program you often need the operating system support, because you may require memory, you want to allocate memory for variables, right. Because if you think of the microarchitecture that we have implemented, there are only a few registers, but your program could be using a lot of variables, right. It could be using 20, 30, 100 variables, 1000 variables, right. And there has to be some way to store those variables in the memory, and based on requirement you need to fetch them, right. And the high level programming or the high level program that we have written, we do not know what will be the number of registers, for example, in the underlying processor where your program is going to be executed. Suppose you write a program for bubble sort, right. You do not keep in mind that how many registers are going to be actually used in the computer where the bubble sort is going to run. You don't even know on how many elements your bubble sort is going to be run on, right. So those are the things that are actually required not even at compile time but at runtime, right. So the operating system gives you a lot of runtime support. Runtime support. Okay. So it has to know details about the memory, right, the cache memory and so on. You will be taught about all these things in an OS class. Compiler also needs to know about the machine's exposed ISA, right, what is the instruction set architecture, right. Then I told you that this ISA is going to be realized. There could be many realizations, and one realization is a particular platform, right. And the compiler need not know, or the software programmer need not know that how is this microarchitecture implemented. As long as it implements the same ISA, the compiler is not going to complain, okay. But sometimes for a high level programmer, right, the person who is actually writing the software in, let's say, Java or C or C++, it sometimes helps if he or she is knowledgeable about the underlying ISA, right. The program can be optimized if you know what is the target architecture on where your program is going to run, okay. So it is not mandatory. For example, I was telling that the programmer need not know that how many registers are there in to write a bubble sort program. All of you have written bubble sort or any program like a binary search or whatever. It is not necessary to know, but in certain cases, if you know, right, your program can become smarter, because in that way you can make sure that certain parts of the program are very friendly towards a certain instruction set, right. So if I want to avoid, let's say, floating point computation, or if I have the instruction set architecture supports floating point computation or floating point multiplication, I could take advantage of that, right. If I know that that support is not available, I want to make the program in a certain way such that it is makes the most out of the underlying system and does not overwhelm that, right. So that is a trick, that is a very important practice programmers might need to write more efficient systems code, right. So sometimes this breadth of the knowledge is really useful for systems programmers, okay. If you develop things that are closer to the hardware and you are really looking for performance benefits, okay. So then we talked about microarchitecture, and microarchitecture is realized in terms of the digital logic that we built, combination and sequential, and this basically built with logic gates, another abstraction, and these logic gates are used, logic gates are made using a series of or a network of transistors put in a certain way, and each transistor being abstracted as a switch. And again, there are further details that I don't want to go into, that why does a transistor act as a switch, under what conditions a transistor could be acting as a switch. We can stop here, right, and that basically gives you the hierarchy. Now coming to the content, right, I would like briefly mention whatever we have studied primarily in these two parts, right. There is not much, but I mean the gist was covered, right. I try to position the entire course in the domain of knowledge that you have primarily in this domain, right. You are most of the things that you had been doing is more algorithmic or implementing those algorithms in a high level programming language. This was primarily taking that code and trying to see that how that code runs on the underlying system, right. That was the focus of this course. So, in terms of combinational logic, if you remember, what you need to really remember is we can use Boolean algebra constructs to build logic circuits. That is the main crux, right. So, we use Boolean algebra, right, the axioms of Boolean algebra, right. We borrow from them and we realize those things in a logical circuit, right. We basically create logic circuits, okay. And primarily there were certain things that has to be known, some jargons. For example, you need to know what is a truth table, right, what is a set of inputs, and for those set of inputs what are the set of outputs. Then after that you want to also summarize these truth tables in some canonical expressions, in form of some canonical expressions called the sum of product or the product of sum. So, these are not optimized in terms of the number of gates, right. Based on how many outputs are 1 in the truth table, those are going to be the mean terms for your SOP expression, okay, and you can further simplify that, okay. So, this is a SOP expression we have studied. What is a POS expression we have studied. We have also studied simplifying them, right, simplifying the SOP expressions or a POS expression, right. We can use the Boolean algebra axioms to simplify them. Also, we had a method called K-map, which is more of a geometrical approach to group together A and A bar or X and X bar and get them thrown out from the simplification or the simplified version of the equation, right. So, X plus X bar is going to be 1, so it does not matter, right. So, K-map was an attempt to do that, okay. So, this was primarily the Boolean algebra and how to use Boolean algebra to simplify logic circuits and so on. And after that we looked at a few standard combinational circuits, right. So, standard combinational circuits, right, and those were things like let us say half adders. Then we looked into full adders. Then we looked into very important, it's a very important tool for any digital logic design, multiplexers and decoders, right. So, with multiplexer we also looked into the inverse of that, which is a demultiplexer, demux, and encoders. The other thing is basically your like encoders, okay. There could be other things, for example comparators, right, but these were the standard ones. What we taught you is basically given a set of inputs and outputs or given some kind of a problem, you should be able to come up with the truth table and design the circuit, right. You basically have to come up with a truth table for a problem and design you can come up with the SOP expression, or you can directly use the K-map to get a simplified expression and implement the circuit, right. And there could be certain cases where we would ask you to, or not ask you, you would be required in a real life design you will be restricted by a few set of standard combinational circuits. You cannot use anything that you feel like. Let us say you cannot use a huge XOR gate that has let us say 5 inputs, right, or you cannot use an AND gate that has 10 inputs, right. Often we want to break up the design, or sometimes we cannot use any gates that you feel like. Maybe you have to use full adders, or you have to use multiplexers or decoders to realize those circuits. Those could be the constraints that are posed to us. Okay, so basically truth table to a circuit and also use of standard combinational circuits. Then we went to sequential. This was combinational logic. Then we went to sequential logic, and the main thing that is different from combinational logic is that the previous states, the previous output also matters now, right? It's not only just the input to the output mapping, but once you have an output, in the next time the circuit is interrogated, the output is going to also depend on the previous state of the circuit, right? So you definitely have a concept of memory. Okay, and we looked into various kinds of this sequential circuit elements. The fundamental element here is a latch or a flip-flop, right, which is of course made with gates with some feedback, but this is better to think of sequential circuit in terms of latches or flip-flops. Okay, so these latches or flip-flops were of various kinds. There is a difference in between what is a latch and what is a flip-flop that you should definitely know. So we have a concept of an enable signal. Often it could be like later it evolved into a clock signal. So when the clock is high, latch is triggered, right, and the clock is high for a finite period of time, and the clock is not high for another finite period of time, right. So if you think of a clock signal is like this, right, and that is basically a latch which is basically level triggered, right. So this is basically level triggered, and the flip-flops are not really level triggered, and we discussed why it is also important to trigger the circuit on edges, right, and what are the advantages of doing that. You should refer to the corresponding sections. So this is a positive edge triggered flip-flop, where the state is going to be determined by the transition of the clock from the low to high. It could be from high to low also, that is called a negative edge triggered flip-flop, right, or a negative edge triggered circuit. Right, we mostly followed positive edge trigger, that is the clock going from low to high. So this was the fundamental building block of our sequential logic design. We started with RS or SR latch, then we looked into a D latch, then we also looked into a D flip-flop, then we looked into a JK. I would say they is still referred to as a JK flip-flop, but it's mostly like a latch, and it also suffers from this problem of race condition. Okay, so it's mostly acting as a latch. Okay, so to remove those race condition, we had to design something which is like, in a true essence, it's a latch, it's a flip-flop, which is basically the master slave JK flip-flop. Right, so typically master slave JK flip-flop will be used for most of our designs, or a D flip-flop will be used for most of our designs. Okay, this is the building blocks, and with that we did several things. One was design of synchronous sequential circuits. Okay. So in the design of synchronous sequential circuit, you need to keep in mind that all that flip-flops are triggered simultaneously. So the clock input is common to all sequential elements. Okay, this is extremely important. In case of asynchronous sequential circuit, this is not true. You can take the output from some other sequential element and put it as a clock to another element and so on. The analysis becomes much more, I mean, it's different. I would not say involved or something. There is a different technique to do that. We have not covered that in class, right? whatever we have studied, apart from some very simple asynchronous counters, where it is like asynchronous circuits makes the life easier, all the analysis that we have done was for synchronous sequential circuits, right? And we looked into several examples, like we looked into counters, right? And these counters will basically be counting values up. It could be an up counter, it could be a down counter, it could be any sequence that the counter counts, and based on how many states are there in the counter, you have to determine the number of flip-flops. So the number of states, you need to understand how many states are there in this particular counter or in this particular sequential circuit, and the number of flip-flops, right? If you have n states, of course you are going to require at most log n to the base 2 flip-flops, right? So this is important, and you also have to design the entire state table, state transition diagram of a particular problem that you have been given, right? A sequential circuit design that you are doing. It could be a counter, it could be any kind of a counter, right? It basically has to go from a state to another state. It's a state transition diagram. For that, you basically have a current state. This is a very important table that you need to understand or kind of retain in your memory. Current state. So this is the current state of the circuit. The current state of the circuit, it could be a 3-bit state, it could be a 2-bit state, it could be a 4-bit state, depending on the number of bits in the state, right? So the number of bits in the state is basically log of the number of states to the base 2, which is basically the number of flip-flops. Okay, so if you have, let's say, 3 states, you are using 3 bits in the representing the state, you are going to use 3 flip-flops, right? So it could be this could be S0, this could be S1, and this could be S2. Then you also have something called an input. The input could be a one single bit, it could be 2 bits, and so on. Then you have the next state. Then you have the output. Sometimes you are not given the output explicitly, but often there could be situations where you have a next state and output is a function of the next state, right? These were discussed in class, right? So this is S2 plus, often we call it. This is S1 plus, this is S0 plus. This could be basically an input, and this is an output. So this is a table that you need to draw, right? So let's say you are designing a counter that counts like this, right? So 0, after that it goes to 2, after that it goes to 5, after that it goes to 7, and back to 0, right? And you have to design this counter. We have looked into how to do that. Let's say you are at, you have to fill up this table, right? At a point you are at 5, which is your current state, looks like this 1 0 1, right? And in this case, there is either there could be an input explicitly mentioned, or it does not depend on the input. It could be a don't care also. Okay, so 1 0 1, and it basically goes to 1 1 1, right? What you need to basically figure out here is not the human given inputs, but what will be the inputs to the inputs from the flip-flops that we are using. Okay, so in this case there is no external input, right? That some human being is given to the circuit, is giving to the circuit that I am putting 1, then it only goes to 0, otherwise it goes to 5, nothing like that. It's whenever there is a clock pulse, 5 will automatically roll to 7, 7 will automatically roll to 0, 0 will automatically roll to 2, and so on, right? So what has to be defined is basically the flip-flop inputs. So here there are 3 flip-flops. Suppose we are designing it using a suppose you can do it either a JK flip-flop or a D flip-flop. If you are using a D flip-flop, so there is D2, then there is D1, and then there is a D0, right? So if I want to go from 1 to 1, the D flip-flop input has to be 1, right? All of you know this. And if you are using a JK flip-flop, it is going to depend on the state excitation table of that particular flip-flop. Suppose this is 0, right? This is 1. So if instead of a D flip-flop we are using a JK flip-flop, so it is 0 to 1, right? So this is going to be a toggle. You have to use the corresponding entry of the excitation table. Okay, So 0 to 0 is 0x, 0, 1, 1x and so on, right? 1x means don't care. So depending on what is the state transition that you are trying to do, you have to fill up the inputs. Similarly, you could be either given an output or you may not be given an output. The output is typically a combinational logic on the next state, right? So if the output will be 1, 0 something, right? So this value has to be computed using the outputs, okay, sorry, the output that is coming out from the state output. Let's say 7 is 111, 5 is 101 and so on. You can take those flip-flop outputs and create the output of the circuit. So this is pretty much the exercise that we have done in case of sequential circuit designs, and we have looked into various kinds of counters or a general strategy to design such sequential circuits, right, synchronous sequential circuits. Apart from that, we have looked into ring counters, Johnson counters, as well as BCD counters. Okay, these are the three types of counters that we have looked at. We have also looked into registers, which is more of a memory holding element, registers and shift registers. Okay, so this is the kind of treatment that we have done in case of sequential circuits, and this would have been like primarily enough to build the very simple processor. So the last part of our course, which we recently covered, so this should be fresh in your memory, is the processor. And I will not go into details because we have just recently covered this. So you have to think of the various elements that are there, and there is an assignment that has been given to you as a part of the last week, right? Although it is optional, but that is going to give you a maximum benefit if you try designing it to some extent. Maybe it is not going to work in a complete form flawlessly, but it is going to give you a lot of experience in understanding the working of the processor, right? So for the processor, we looked into a very important concept of this ISA, right? I kept on talking about it even in this session, and followed by the assembly code implementation of certain programs, assembly level implementation, okay, of certain programs, right? And after that, we have also looked into the microarchitectural details, the microarchitectural details, and which mainly contain information about things like a register file, the bus, right, the ALU, and ALU plus status register, then a program counter, then an instruction register, memory address register, plus optionally the memory data register, right, and instruction register plus instruction decoder, right. So this was primarily the data like involved in the data path of the processor, and then we also had a very important thing called the control logic. Okay, so the control logic could either be implemented in hardware, or it could be programmable control logic, which we called as a software control logic. Okay, software defined control logic, where we program some kind of an ROM where we implement all the control signals or the micro instructions that are going to be issued when an instruction gets executed. So this was a multi-cycle and non-pipelined multi-cycle processor. Okay, so this is basically putting together all the things that we know that we have studied earlier, right? So for example, ALU is basically a combination of an adder, addition, subtraction, logical operations and so on, right. This program counter is nothing but a counter, okay. Instruction register, memory address register, status register, these are all registers, right. So these are the things that could be typically we can just borrow from whatever we have studied in the sequential logic design, where we studied about registers, and we can simply use that, right. Control logic, you can either implement it in hardware, it is going to be kind of an exhaustive design, right, where you have the various micro instructions outputs, those are going to be output as the like basically you have a truth table, right, in the hardware design. So if you remember, there was an instruction opcode. So for every opcode the micro instructions are going to vary, and within that opcode you are going to have a series of steps, and every step is indicated by the T state. So depending on how many bits are there, let's say if there are 3 bits in your T state and 4 bits in your instruction opcode, this is going to be a enormous truth table, where you are going to have 4 plus 3 7, so 2 to the power 7 is 128 different rows, right. And for every opcode, here you are going to have 2 to the power 4 or 16 opcodes. You are going to have some, these are your control bits, let's say control bit n dot 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 control bit 0, right. So these are your control bits. So you can take up every control bit, let's say control bit I. So you will see control bit I, let's say this is 1 here, 1 here, 1 here, and so on. You can always come up with a SOP, like the sum of product of control bit I, or you can then do a K-map and simplify it, right, or simplify it in some other means, right. You cannot probably do K-map, there are too many variables. Here it is 7, but it can be much more larger, right. The inputs can be of much bigger size, right. The opcode might be 8 bits, right. The T state counter may be 3 bits, but the opcode will be definitely larger for a real life hardware, okay. So this is just implementing all the things in hardware. The other thing is that you can instead use the truth table directly embedded in memory, right. So instead of having designing a truth table like this, what people do, they will take this part and use this as an address to look up memory, and instead of having 128 rows in the truth table, which is basically implemented in terms of hardware, you can simply store the entire truth table like Cn to C0, 128 rows of them directly in the ROM, right. So this is your ROM, and if I say give me the 57th line is going to come from this combination of a certain opcode and a certain T state. You are going to go to the 57th line and basically pop out the corresponding micro instruction or the control word, okay, micro instruction or the control word or the control word, okay. So this was about the control. I have also showed you how to automatically generate that or programmatically generate that those control words using a program, right, a Python program or a C program. So I would definitely suggest that you attempt the last exercise, which is a simulation of a processor. Please start with an ISA, right. The ISA is going to be provided to you. This is basically the opcode plus operand combination, that will be some table that will be provided to you. So this is going to be like how the add instruction is going to look like, what is the opcode for add instruction, what is the opcode for LDA instruction, and so on. So you can expect that we are going to have a 4-bit opcode and 4-bit operand. I am restricting this to 4 bits because you can use the ROM that is there in circuitverse to implement, and it only has 16 memory locations for reading from the ROM, and I am specifying ROM for a very particular reason. The ROM that is there in the simulator, you can look at the contents of the ROM visually, right. So it looks something like this. This is the 0th location and this is the 16th location, right? Okay, and you can always use a RAM or let's say an EEPROM or something where you can still there is a way to write, right? RAM you can definitely write, but I mean you won't be able to see what exactly is there in the RAM unless and until there is a way to read from the RAM using a separate circuit, right? So it's much more easy and more interactive. You can easily debug what is going on if you are using a ROM. The only bottleneck of circuit bus, or it's not a bottleneck of circuit bus per se, of course ROM you should not be allowing it to write because it's a ROM element, read only memory, right? So you cannot do something like an STA instruction. Okay, so STA is not allowed because this is a ROM. Okay, LDA is allowed, so you can load from the memory to the accumulator, like load the accumulator from memory because you are reading. So apart from STA, you won't be facing any other instructions that will have issues, but I would say include STA as a part of your control logic, because if you replace the ROM by RAM, then it is going to work, right? So 4 bits for opcode, but here also in the first try you don't have to use all the 16 opcodes. You can assume the first one to be 0 and the next 3 are your opcodes. So here you can start with only 8 instructions, right? So these are the 3 least significant 3 bits in your opcode, which is basically 8 instructions, and the most significant bit is 0. Okay, you can start that. If you have confidence, then you can go to using 4 bits for the opcode, right? And operand, of course, there are 4 bits. Either if it is a memory instruction, it could be an address, or if it is an immediate instruction, this is going to be data. Okay, so either data or address, right? And that is probably all, right? So again, summarizing, you got an idea of how to position this course in your entire curriculum of computer engineering, right? Where you start with algorithms and how these algorithms are implemented using high level programming languages, and how the compiler and OS takes it over and launches your program on a target architecture. And this course was primarily is a journey towards starting to build this architecture, right? How do you have enough prerequisites such that you can start building an architecture? We have never built any real life architecture as a part of this course. Whatever we have done was primarily getting some practice or a warm up in getting acquainted with the various constructs that a architecture is going to have, right? A real architecture is going to have a program counter. They are still going to have an ALU, right? They are still going to have an instruction register. So every component that has been introduced to you are real, just that the ISA is too simplistic. A real life ISA is going to be more complicated, and the microarchitecture is going to be much more involved, right? So we just had 3 general purpose registers. In even a cheap CPU is going to have maybe 20 or 30 registers, right? So even the simplest of the simplest, very low cost CPUs are much more complicated than what we have studied, right? So this is a beginning to, if you want to inculcate more on this, you can always look into a little bit of computer organization and computer architecture, right, which has been started in this course, but we did not get time to look into much more in-depth details. And some part of it is like particularly related to memory is going to taken up by a course on operating systems. If you register for this course on operating systems, you will get a little bit of more details about how memory is being handled by a program that is running, right? Particularly concepts like processes and so on, how an operating system is going to run various programs simultaneously at the same time on the CPU, right? So operating system is basically a course where you will see given the underlying architecture or given the underlying resource of the CPU, how that resource is shared, right? Not only the CPU but also the memory. The memory and the CPU is shared among multiple programs that are running on the computer, and we are trying to make the best use of it, right? We don't want the CPU to be idle, right? We want the maximum utilization of the CPU and maximum utilization of the memory, such that every program is going to give you a better performance in terms of latency, in terms of like interactivity, right? So if you are having an input output system, it has to be responsive and so on. So those are the things that is going to be covered on the OS course if you register for that, right? So good luck. Hope you have been introduced to a processor architecture if you have not been introduced to it earlier, and hope you have enjoyed it, right? Please go through the assignments one more time that has been given to you, the weekly assignments and the quizzes that was given to you, quiz 1 and quiz 2, for preparing for the finals, right, the end semester examination. And also do not ignore the implementation level aspects, right? The week 11 and week 12 were implementation aspects. Week 11 is you have to do as a part of your credits, but week 12 is again optional. But I would definitely tell you to give it a try, because the concepts are only going to become clear when you implement that, and that is going to be, those concepts are very useful for your end term exam, right? So I will keep it till here. So thank you for registering for the course. Hope you have had a good learning experience.